And what we learn from, mostly I've talked about the old spectrographs, what we learn from doing surveys with low resolution spectrographs and how things appear when we look at galaxies with high resolution, and we can study, feedback and galaxy superwinds and properties and the covering of the atomic ISM, which is all believed to be important for the transfer of Lyman-alpha and the emission of Lyman-alpha. Today we're going to complete that observational picture as determined by the Hubble Space Telescope. So we'll look how we do imaging in the ultraviolet of emission lines. It's very hard to do narrowband imaging on a telescope that doesn't have any ultraviolet narrowbands, so we have to find some cunning way to synthesize them. And I'll talk about obviously the astrophysical results of these Lyman-alpha imaging studies. That boils down to surface brightness profiles, resolve different regions of galaxies, the Lyman-alpha scattering halos that we discovered at low Z. And I'll talk some about the dynamics and 3D kinematics of both ionized and atomic gas. Try and just complete the observational picture before we can go in, try and assemble all these quantities and all these many different trends that we see in the final lecture. So these are some presentation of the motivations for doing these. This is a very old slide now. You see it's been copied and copied and copied, and the quality is going down. But this was the sort of state of high-resolution spectroscopy. You see a variety of line profiles, and when you put a small slit on a galaxy, you see profiles that look like this, for example, where you see a bright Lyman-alpha emission line, and that is easy to interpret. You know there that you have Lyman-alpha, and that's great. But what you don't know is what happens to these photons down here in the absorption line, or here in this very deep absorption line. All you know is that when you put a slit on a galaxy or a small aperture and take a spectrum, all you know is that Lyman-alpha photons are not coming out from here. You don't know whether these photons are going to be absorbed by dust. You don't know whether they're going to be redistributed in frequency and emitted in this part of the line profile as classic P Cygni. You don't know if they're going to be scattered out of the line of sight and emitted somewhere else or absorbed by dust somewhere else. So the problem is that we just don't know the fate of these photons when they diffuse both spatially and in frequency. So we'd like to build up a clear picture of the morphology of galaxies in Lyman-alpha. And the way you do this, where you build up an image of emission line, almost always, is by doing narrowband imaging. And HST, as I alluded to 3 minutes ago, doesn't have any narrowbands. So what we do is we use the filters that we have. This is how we began in cycle 11 of HST, which is now 13 years ago, I think. In the ultraviolet, on the solar blind channel of ACS, there are these two filters, right? There's this 122M medium band filter that was designed and is there on the telescope for imaging of Lyman-alpha in the rest frame. This is a pretty broad filter, right? It's 100 angstroms wide, so that's why it's a medium band filter, which at 1200 angstroms gives you a filter which is full width half max divided by its central wavelength, about 10%. This is not narrow for a narrowband filter. If you take a 50 angstrom wide filter like an oxygen 3 filter in the optical, that's 50 angstroms wide at 5000. That's 10 times the contrast of the kind of filters that we have here. So that's it's difficult to work like this. And moreover, when you have a filter, an online filter centered at 1200 and an offline filter centered near 1500, that's 300 angstroms difference between offline and online, which is another factor of 25% in the wavelength scale. This scaling between the flux you would expect from continuum processes offline and online is going to be quite significant. It depends on knowing the spectral shape. Here, this filter that transmits Lyman-alpha has a peak instrumental throughput of 0.01, that's 1%, so for every 100 photons that enter the telescope, only one causes a photoelectron on the detector. Could be better. And also this big line here, this line, if it transmits Lyman-alpha in the rest frame, that means it also transmits Lyman-alpha from the Earth's atmosphere. This geocoronal Lyman-alpha line, which increases the background, increases the noise, and ends up with a not particularly efficient configuration. And since we have a not particularly efficient configuration, obviously we use it. And this is how we first attempted to image Lyman-alpha. So it's a paper by Daniel Kuhn from 2003. And here we targeted 6 in total, but here 2 famous starburst galaxies, Haro 11, SBS 0335. I've talked about both of these already. And you see offline images here. That's obtained in this big, reasonably high throughput Longpass filter. And online images here, they look broadly the same. This one is composed of 3 bright star-forming regions. We call them A, B, and C. And when you make a general assumption, assume the continuum slope to be of a certain shape, you can subtract the offline flux from online, and you come up with Lyman-alpha image, or what you believe to be a rough Lyman-alpha image. And it shows that from this star-forming region here, no Lyman-alpha, these images are all inverted, bright Lyman-alpha emission from up here, and some fuzz around there. This one, for which we've already seen the spectrum, is one of damped absorption, indeed shows strong absorption in the center, maybe a hint of Lyman-alpha emission around here. So this is very rough work, but it's how we began. And then, after a few years of playing with this, we realized that the same camera also contains these long-pass filters up here, right? So instead of using this little filter down here, we take these long-pass filters. These are basically triangular. They're just cut-on filters, so they transmit everything redwards of their cut-on wavelength. And this red wing of the filter here is just a decreasing quantum efficiency, QE of the detector. And what we realized was that if you take individual pairs of these filters, like this one minus this one, or this one minus this one, you release reasonably narrow, synthesized narrowband filters that you can capture Lyman-alpha with. The advantage of doing this is that the narrowband that you release ends up having a reasonably nice shape, broadly, broad is not a good word to use for these filters, but that they cut on, they go up very quickly, they kind of flatten top, and they fall quickly. They have little wings there, of course. The peak throughputs are much higher here, so here the total throughput is about 5% instead of 1. And all we have to do is select galaxies that lie at the right redshift to push Lyman-alpha into the bandpass that we want to use. The advantage of going to slightly higher redshift is that you get this nasty geocoronal emission line out of the bandpass, and that's going to reduce the background. And just to compare these two methods, this is another galaxy that we observed in our first sample. This is Lyman-alpha continuum subtraction. You see fuzzy blobs of Lyman-alpha emission there and there. And this is using this filter minus this filter. And this image here is obtained by using this long-pass adjacent pair technique. In this case, it's very clear from the images. They're on exactly the same intensity scaling. This one, you have a nasty, nasty background, and this one, it's all pretty good. In this case, you improve signal-to-noise ratio by a factor of 5 using just 3/5 the observing time. So that's the strategy that we use for at least isolating the Lyman-alpha line. It's unfortunately still a bit more complicated than that because we don't know what shape the continuum has, and if you don't, this is really a spectral region where the continuum can take any shape from being particularly blue if the stars are young and unreddened, to particularly red if they are older or if there's a lot of dust in the galaxies. I plotted here on top of these band passes. I apologize for it being a bit messy, but the blue line here is a young and unreddened starburst, very blue. And in any continuum subtraction, you're going to want to know how much flux there is, how many photoelectrons you have because of continuum process. So you have to scale the offline filter to the online filter. And you see, because this one is particularly blue, for example, you put in a little bit of dust here, EB minus V of 0.5, you make the same spectrum particularly red, and this is going to result in a very different scaling factor by which you have to scale one filter to match the other one. And not only is this going to differ a lot from galaxy to galaxy as a function of the stellar population, but when you have high spatial resolution and you resolve galaxies down to scales of a few tens of parsec, 40 parsec I think for the nearest one, this can easily vary on scales, and you can have galaxies, starbursts are very clumpy, they don't all have the same stellar age, the dust distribution is not homogeneous and the same everywhere. Just to exemplify that, I'll give you a feeling for that. Here's the same galaxy again, here's a beautiful HST multicolor broadband image, and this is a map of the UV continuum slope beta, so it's just this power law parameterization for the continuum. And here is a map of that UV slope, scaling between beta of -2, which is roughly what you expect for an unreddened young starburst. So this region down here, super blue. This region up here, you can see the dust, right? And up here, super red. This shows you, very clearly how the stellar continuum varies as a function of position. Here's an example of this I computed using spectral synthesis models. And this is the UV slope, covering a pretty long range on the x-axis, but between -2 and 3 is in the box here. This is UV slope. Each one of these is a track of age for a different reddening. So each one of this is galaxies getting older, and down here each one of these is another track for the same with a different dust reddening. And you see that this continuum scale factor may vary by a factor of at least 50% over this range of colors that we see here. And this can have absolutely devastating effects for the continuum subtraction and the estimation of the continuum flux at Lyman-alpha when you're doing imaging. And just to demonstrate this is our sample of 6 galaxies here. This is an online filter up top, offline filter down there. And I'm going to produce continuum subtractions assuming that the UV continuum has a slope of -2 in beta. So blue, flat with a beta of 0, flat in F lambda, and red with a beta slope of +1. All perfectly within the realms of possibility for star-forming galaxies. And here, if you have a very blue slope, scale factor is large, subtract a lot of continuum, and you end up with Lyman-alpha absorption in every case. When you assume the continuum slope to be flat, you get some hints of Lyman-alpha emission here. This knot is starting to emit Lyman-alpha. Appear to emit Lyman-alpha. Kind of flat, and a lot of fuzz in this galaxy over here. It's become a Lyman-alpha emitter, I believe Lyman-alpha emitter. And when you assume the continuum slope is red, your scale factor becomes small, and you get Lyman-alpha out of your galaxies, and you don't know what's right. And because I have recently learned to do PowerPoint animations, we don't know which one of these is right, if any. And of course, actually none of them are right because they've assumed the same slope for in every pixel, and that isn't right either. So I spent some time playing with this. I spent a very long time playing with this when I was a PhD student, taking data for this galaxy, ESO 338, where we have also lots of HST off-band imaging. So we have images in the near UV and UB high filters. We could produce image here. We put a STIS slit over here. And this is the STIS slit here, so we know spectroscopically what the Lyman-alpha is. Here you actually see the geocoronal line here. This is the continuum from that bright source there. But you can see, if you look just below the geocoronal line here, a few tens of pixels down, you see this fuzz here. And this fuzz is Lyman-alpha emission, and this is how you test. You know what you're going to get is right because you have it in a spectrum. This is just some scale factor map that I produced. This is a result, and what we discovered was that we need to do some spatially varying continuum subtraction based upon many other filters offline to really characterize the shape, behavior of the stellar population. And I don't want to go into the detail too much, but we wrote a load of software to try and do this for us. We obtained more HST imaging in various bands between the near UV and the I band, narrow bands at H alpha, H beta. And then we do, in 8-band HST imaging, then we do a set of population synthesis, SED modeling. We use Starburst 99 models from Klaus Leiterer. And in every pixel, we measure the H alpha, H beta flux, and we determine how the nebular gas behaves. And we subtract the nebular gas spectrum from all of our broadband images. And in each of our broadband images, then we do a multi-component fit to the stellar spectral energy distribution. And this, in every pixel, gives us a map of the age of the stellar population and its mass, and EB minus V, the stellar EB minus V, stellar attenuation. This is what's giving us the shape of the UV continuum. So we're putting all these things together, a gas spectrum, a young stellar population, an old one. We add them all up, estimate the shape of the continuum near Lyman-alpha, and we convolve that with the bandpass, and then we subtract that to get Lyman-alpha. Here we get all of this stuff in addition, so we get maps of age, mass, dust reddening, nebula dust reddening. We can constrain the actual amount of mechanical energy that's been returned in every pixel from supernovae and stellar winds. We can produce maps of the ionizing radiation production, so maps of how a galaxy looks at 900 angstroms or integrated over the whole ionizing continuum. And we can also produce, most importantly, images of Lyman-alpha. And we have this code, it's called the Lyman-alpha extraction software, designed to do this, and we use it for all of our 50-odd galaxies we've observed in Lyman-alpha. And if anybody is interested in doing Lyman-alpha imaging at low Z, then this code is not freely available, but you can absolutely use it. We're not going to distribute it because then we have to support it. But if you are interested in doing this, then please get in touch and we can discuss how to do it in detail. So these are the first pilot study here. We selected famous starburst galaxies with a range of metallicities and a range of luminosities. We picked emitting and absorbing galaxies. These were first published in a paper by, we picked just a range of famous starbursts. These are all from the IUE catalogs. 4 of these 6 entered the determination of the Calzetti extinction law. This is not showing up in the light in this room. These are the first images of Lyman-alpha. It doesn't show up at all. In red, this is the standard color scaling that I've shown before. So we show UV continuum in green. It's where the ionizing photons are being produced. They make the nebulae we observe with narrowband H-alpha filters. That's what you see in red here. And in blue, you see Lyman-alpha. There's better images coming up later. Don't worry too much about it. It's the bottom part that's too light. I bet, it's coming. It's probably better when I have... So this is an example of a galaxy called HAR 11. It's a famous one. Look in the UV continuum. We've shown it before, but it has bright star-forming knots that we call ABC. Look in H-alpha. This is how it looks in Lyman-alpha. It's a big fuzzy blob. Mostly, there's a bright patch of Lyman-alpha emission associated with this star-forming condensation here. This is a massive star cluster. Close to a star cluster. It's 10 to the 7 solar masses. Has age of about 10 million years. You see, actually, in these regions where the H-alpha is brightest and the intrinsic Lyman-alpha is being produced mostly in these bright H-alpha regions, actually there's a fair bit of absorption there and the Lyman-alpha is becoming negative. So this is probably something to do with the varied properties of the interstellar medium in this galaxy. Not every part of a galaxy is going to be the same. We can produce, for example, surface brightness profile in Lyman-alpha. It goes like this, it's bright in the middle, it decreases, seems to be falling off in like this kind of. Here it's radii of about an arc second. It's starting to flatten. You introduce this, you see this scattering fuzz around here. There's a bright spot of emission there, which is that part in the middle, and there's a fuzzy halo, which you're seeing here. It's in log radius here, log flux. This bright part of Lyman-alpha emission here, of course, we have H-alpha images, so we can go and compare in every pixel the Lyman-alpha surface brightness with the H-alpha surface brightness. And this is a contour map of all the pixels where we do that. So just take the blue image. This is a map here of the blue image on the y-axis and the red image on the x-axis. And it's a distribution, a contour map of all the pixels. So there's almost 1 million pixels in this image. This is where they fall. You see this red here. This is the case B recombination ratio, Lyman-alpha over H-alpha of 10. And this fuzzy spike up here, there's a distribution here, actually follows the case B recombination ratio. So here, radiation, Lyman-alpha is being emitted from here, very close to case B, with setting a limit to the upper envelope of these pixels, and there's a large number that here dropping in Lyman-alpha surface brightness, which is where they're being either absorbed by dust or scattered out of the line of sight. There's a huge number of pixels down here. This is where Lyman-alpha over H-alpha is below the recombination ratio. This is where you can have dust reddening or scattering out of the line of sight. There's also a fair number of pixels up here where Lyman-alpha over H-alpha is not 10 but 100. This is pixels from the halo scattering back into the line of sight. If you look for the peak here, the peak of this distribution is in here somewhere. It's the average. That is at about Lyman-alpha over H-alpha 0.2. That is escape fraction of something like 20%, which is the global value for the galaxy. We can also start to dissect the galaxy in more detail using H-alpha and H-beta narrowbands. We did this from the ground in the beginning in this study, and you can measure here, you compute H-alpha over H-beta in every pixel, you compute the Lyman-alpha flux in every pixel, and this is Lyman-alpha flux, and the brightest regions are these ones up here, and that's coming from here, this bright spot. This region we actually see significant dust attenuation up to EB minus V of 1. It's a paper by Hakim Matek, who's now left. And here in these absorbing pixels, we actually see here, where the Lyman-alpha is absorbed, we actually see less the dust attenuation than we see when it's emitted. So we're showing here, when we start to look at galaxies in detail, actually, that same kind of mess that we observe on the global scale is being revealed. There's huge spread, galaxy doesn't behave in a way that we would really expect it to. This is a map of the ionizing continuum. You just take the spectral energy distribution and fit it. This was done for this galaxy Harrow 11 in the beginning because in 2006 it was determined to be a Lyman continuum leaking galaxy, and we wanted to estimate what Lyman continuum morphology would look like. And this was the state in 2009. We published this catalogue paper, and we had a sample of 6 galaxies. And we didn't like a sample of 6 galaxies because they were all hand-picked and very difficult to generalize. So we began the Lyman-alpha reference sample. We put together a team. This is the team. Very many of us. People come and they go. We went to the Galax catalogues to select UV continuum galaxies over a range of luminosities to make them comparable to Lyman break galaxies. We also went to the Sloan catalogues to find galaxies at the right redshift, to put them into the windows where our narrowband filter techniques would work. We selected galaxies with H-alpha equivalent widths above 90 angstrom. That's to ensure active star formation, make sure we're not dominated by boring star-forming disks that are not producing a lot of ionizing photons and therefore not producing a lot of Lyman-alpha. This is where they all lie on the BPT diagram. They're all sitting on the star-forming sequence, more or less. We threw out anything that could be an AGN based upon BPT and emission line width diagnostics. This is how the galaxies look in the Sloan. They're all blue. There's a lot of mergers here. They're not particularly regular. Blue, some of them pretty compact. There's a green P, depending on your definition, I think. When you go and look at them with HST broadbands, you see of course, spatial resolution goes up by a factor of 10 and they look much nicer. You start to see the details. We look in Lyman-alpha. They look like this. This is the same color coding I always use, UV in green, Lyman-alpha in blue, and you look at this and there's something that sticks out at you, right? Something leaps out at you. And that's that Lyman-alpha, H-alpha in red is where the Lyman-alpha radiation is being produced. At 10 times the intensity of the H-alpha radiation. But it's coming out in blue, not in the same space, not in the same position. In these cases, some people in our institute like to say that the galaxies are swimming in a bath of Lyman-alpha. Here's just a zoom of a couple of galaxies, Lars 1, Lars 2. Let me get this right, Lars 5, Lars 7. Lars, these are the compact ones. This is Lars 14 and 12, I think. Lars 9 and 11. And you see always that the Lyman-alpha is more extended, sort of following the distribution of star formation, following the distribution of non-ionizing radiation, but in a big fuzzy ball that surrounds it. And there's the sample again. So with these images, I can produce surface brightness profiles. For example, I can compute aperture curves of growth. Here on the y-x-axis, we have radius of each galaxy. I've now put all the last sample on one plot. And you see, as with all curves of growth, you make the aperture bigger, you add up all the flux, it comes inside that aperture, then they increase. You get bigger aperture, you get more Lyman-alpha, or more of all the radiation that you add up. And that's the case for all these galaxies up here, right? They're growing, and some of them sort of turn over, become relatively flat curves of growth after about radii 5 to 10 parsecs in kiloparsecs. In cases like this, we believe we probably captured the bulk of the Lyman-alpha radiation. There are counterexamples. I mean, not all counterexamples, but there are galaxies that grow much more slowly, and particularly these two large galaxies here. You see the Lyman-alpha flux is still increasing with increasing radius out to radii 20 kiloparsecs. These are the ones that have particularly large halo emission. And there's a really cool example of a galaxy that starts off being a Lyman-alpha absorbing system in the middle. You absorb more and more Lyman-alpha out of the continuum here. And then as you go up and up and up, you go to bigger, larger radii at 10 kiloparsecs. This becomes a net Lyman-alpha emitter. And then the Lyman-alpha emission increases with radius further and further. And this is actually one of the spectra that I showed yesterday with a very, very deep damped Lyman-alpha absorption trough on the central pointing. This is the same thing with equivalent width instead of radius. They all grow. This grey box here at the top is equivalent width above 20 angstroms, which we take as this canonical definition of a Lyman-alpha emitter, how we select galaxies at high redshift. So two of them never become Lyman-alpha emitters. They always absorb. 8 could be detected as Lyman-alpha emitters at high redshift. I'm going to plot some surface brightness profiles. This is now sort of surface brightness in the Lyman-alpha in blue and the UV continuum in red. And what we see in a large number, these are and also fits of surface profiles to the Lyman-alpha and the UV continuum, just like everybody does for galaxies. Surface formula looks like this, right, with an exponential and a radius and a 1 over n, where n is the surface index. And centrally peaked, things very much like this, log axis that's not available in cartoon form. But with n of 4, then you have this de Vaucouleurs profile that's appropriate for elliptical galaxies. And n equals 1 is exponential. And we find here, when we plot the index of the histogram of the surface indices of the UV continuum in red and the Lyman-alpha emission in blue, that they have extremely different, very different surface index profiles. Here we have an average value of 1.5 in Lyman-alpha, close to exponential. And here in the UV continuum we have an average value of 5-ish, which is rather close to the de Vaucouleurs profile. It's also what's been shown in ULERGs. And, well, let's not speculate too much about why it's so large. What's important here is that central peaking, the UV is where the ionizing radiation is being produced and sort of where the energy for Lyman-alpha is coming from. It's very centrally peaked. Of course, it's clustered, the star formation goes on in very dense environments. All this structure is washed out by Lyman-alpha scattering. Scattering is tracing something else. The scattering surface is probably related to the H1, or it will be, has a different distribution. There have also been, now let's not speculate too much. Okay. This structure has gone in Lyman-alpha. I measured the sizes of these halos, the galaxies in Lyman-alpha. You can do the same in H-alpha. Well, this is in the UV, is it? It's this both. Okay. So I measured the sizes in Lyman-alpha, size in the UV. This is in kiloparsecs. These are Petrosian radii. And we can plot the size in Lyman-alpha against the size in H-alpha. And this is the one-to-one line, this dotted line here. And we see, of course, that characteristically like galaxies have about 2 or 2.5 times the average Petrosian radius in Lyman-alpha they do in the UV, and in H-alpha, twice as big. And I can plot this against the escape fraction, for example. And I can see that these galaxies here, this is the extension, so what I've called this relative extension, the size in Lyman-alpha over H-alpha, so how much bigger it is in Lyman-alpha. Plot this against the escape fraction, for example, and the galaxies with high escape fraction, they also appear to drive large halos of Lyman-alpha emission. I don't know why, but they do. We go and observe this sample with optical IFUs as well. So we want to know what we can get the intrinsic H-alpha morphology from HST, but we don't know how it moves. And We don't know the kinematics of the ionized gas, and we just have narrowband filters. So we go and observe them with optical integral field spectrographs. This is an example of Laris 9. It's this Cheney galaxy. This is the spectrum that I showed yesterday with this really, really broad Lyman-alpha absorption profile out here. Don't detect any hints of Lyman-alpha emission in the middle unless you want to believe that that little blip there is a Lyman-alpha line. I'm skeptical. This spectrum was obtained on this central pointing here. This galaxy does emit Lyman-alpha, but it doesn't emit it from here. It emits some regions around here. These star-forming regions do let out some of their Lyman-alpha, but not the central region. This could be related to the gas distribution in this galaxy. It could be related to the kinematics. It could be related to the fact. Let's come on to that in a minute. So here's HST Lyman-alpha image. This is just a showcase for one galaxy. We have observations from the PMAS IFU on Calar Alto. This is a velocity dispersion map and line of sight velocity field map. This observation is done by, that's from Cal, and this is paper by Christian Herentz at Potsdam. We also have H1 higher resolution interferometric observations with VLA config B and C in this galaxy. Actually resolved the H1 in front of the galaxy. Here is the contours of the H1 column density. You see this small galaxy over here, which I had completely ignored when we did the selection and when we did all the previous analysis of this galaxy. A tiny red thing over there contains a big stack of H1 out here with higher resolution VLA interferometry. We can actually start to look at the H1 rotation velocity field for this galaxy. It's rotating this whole thing here is rotating like this, plane of the sky. This thing here is probably interacting with it and sharing an H1 envelope. Maybe that's in part responsible for the peculiar Lyman-alpha morphology of this galaxy. I'll show some other examples of the velocity fields we derive from PMAS. There's some rotation here and here, Lyman-alpha images up top. And from these IFU observations, we can compute, for example, these metrics that characterize the bulk motion, so the shear velocity, just the max minus min of the line of sight velocity field. Also random motion, which is basically just some kind of weighted summation of the velocity dispersion in every SPAC cell. This is telling us about the total bulk motions. This tells us about the total random motions. The ratio of the two gives you a metric of whether a galaxy is dominated by bulk or random motions. Ordered rotations if this is more than one. Dominated by turbulent motions if it's less than one. We plot this for the entire sample. Lyman-alpha H, it's Lyman-alpha H alpha, but it's essentially escape fraction on the x-axis here. The independent, and this shear over dispersion on y here. So when this is high, then the ordered motion is dominated, and these could be described as rotationally supported. These rotationally dominated, sorry. When this is low, below about 1 down here, then you would say that turbulent motions are dominating the ionized interstellar medium. And it's down here when turbulent motions dominate the interstellar medium that we see the strong Lyman-alpha emitters. So here's my list now, which is growing to proportions where it's starting to get annoying, but that's intentional, right? There's hopefully a method in this, but they also have more turbulent velocity fields. Okay, so I'm going to give now a closer example. That's 10 minutes, right? Yeah, I'm probably good. This is a closer look of one of the galaxies now. I want to show some other observations and other things that you can do with IFUs when you have all this Lyman-alpha imaging. This is ESO 338 IGO4. It's what we would call the closest analog of a Lyman break galaxy. Not that star forming, so it's a 0.1L star Lyman break galaxy, but super bright, super compact in the UV continuum. It has a large number of these very bright, massive star clusters, and this one in particular is very interesting. This is what Ernst Lin calls cluster number 23. It has a dynamical mass in one unresolved star cluster of 10 to the 7 solar masses. It has 6 years photometric age by SED fitting. Galaxy is undermetallic, about, well, on the order of a 10th solar. And it was first predicted, expected to be a Lyman continuum leaking galaxy based upon residual intensity in this carbon-2 absorption line here. This does not go black in the diffuse spectrum, and this has been demonstrated by Elizabeth later to be a possible emitter of Lyman continuum. This is the HST image here. I forget which band it is, but the important thing is to note is that there's this cluster here. In red anywhere you have an emission line. I can't remember whether it's H-alpha or O3, but it doesn't matter for this point. The cluster here is sitting inside what appears to be an evacuated bubble, which is probably blown by driving winds into the local environment, sweeping up gas from the ISM. We went to observe this with VLT Muse. Now, Muse has been discussed an awful lot at this meeting in reference to Lyman-alpha, and of course it was one of the main drivers for building it. But, you know, it's a huge contiguous IFU with a 1 arc-minute field of view that spans everything between about 4,800 angstroms and 9,000 and something. So it's not just good for enormous Lyman-alpha surveys, but if you observe a starburst galaxy with it, you get almost every line you could dream of. It has small pixels, 0.2 arcseconds, so you get excellent sampling. It's much better than any other IFU that I have ever used. I finished that sentence, I think, in the right way. So here's a stellar continuum here, very compact. This is observed from the ground with a 3-meter telescope, the NTT at ESO. That's how it looks when you look at that H-alpha line, which is there. Get this right? There. This is a log spectrum here, so it's an optical spectrum in log space, so the lines look unusually strong. See the HST image there in the middle sits inside a huge, huge halo of ionized gas from a paper by Ariane Bick that was published last year. We go and look at the velocity field in H-alpha. You see it's enormously complicated, right? This is not noise that we're seeing out here. This is genuine structure in the H-alpha emission. It's a crazy velocity field. You see long bits here, fingers that appear to be redshifted. These are flowing H-alpha into the board, optical contours there, and you see some apparently outflowing gas in this direction. There's these redshifted top and bottom components here are really kind of interesting, because when we go and look at some emission line ratios, we find these regions also to be super highly ionized. So this is a map, what we're seeing on the right here. This is a map of the index of the sulfur 2 lines at 67 something, divided by the oxygen 3 line at 5,007 angstroms, which has been shown to be a tracer of the ionization parameter in the ISM. Here we're seeing this map, so this is coded in the color here. So when this value is low, that means you have very strong O3 compared to S2. O3 has a much higher ionization potential, so here what we're looking at is gas that's particularly highly ionized. And you see here, this galaxy is blown a hole, it's blown a chimney. The central regions are in here somewhere, really kind of hard to say. The top and bottom here, it's blown out very, very highly ionized channels. It's carved them out. And these are qualitatively consistent with this enhancement of Lyman-alpha that's coming out top and bottom of this galaxy. Could be here that we have highly ionized channels through the interstellar medium that allow the Lyman-alpha to come out preferentially in this direction. It's a working hypothesis right now, but would also be consistent with the galaxy being an emitter of Lyman continuum radiation, has been suggested by analysis of the very far ultraviolet spectrum taken with the fuse. That is a showcase of how we do Lyman-alpha imaging and the other things that we can do with resolved data from ground-based telescopes. Great things, VLT Muse, we're going to have a program observing all the galaxies we can with VLT Muse now at ESO. We're also getting all this optical IFU spectra from Calar Alto in round H-alpha, H-beta, also O3. Of course, you know, I have this silly thing now, this big list of, this number of quantities on here is probably on the order of, well, it is on the order of 10. Our original sample of Lyman-alpha galaxies in Lars was 14, so we're up to as many parameters as we have galaxies, more or less. And we don't like that very much, so we're observing a load more. This is called the extended Lyman-alpha reference sample. This was a program from cycle 22, so the 21. The data are about a year-ish old. It's 28 more star-forming disk galaxies. This sample of galaxies with 8-band HST imaging and Lyman-alpha is going to be 55, or is already 55. This is a showcase here. We have just done the image processing and the continuum subtractions to look at the morphology. We haven't done any measurements yet, but here we're seeing, what we expect, what we've seen before. The galaxies swim in a bath of Lyman-alpha. They all seem to have Lyman-alpha halos, large-scale systems, somehow tracing the atomic gas distribution. We're going to be working on this in the next year, next 2 years. I don't like to leave watch this space adverts, but watch this space. So this is the end. This is everything I wanted to say about HST imaging. UV imaging of emission lines is possible with the HST if you take a lot of care. There are ways of doing it with the existing cameras. We have a suite of software tools that we're willing to share for anybody that wants to embark upon such experiments. We can demonstrate that small-scale properties of things like the dust distribution, as far as we've tested it, seem to be broadly uncorrelated with the Lyman-alpha emission on spatial scales that we can resolve. Lyman-alpha photons are observed to scatter out in large-scale halos, scattering out of the line of sight, depressed Lyman-alpha in central regions and coming out in big fuzzy halos. These scattering halos are observed to be somewhat more extended, twice the size of the UV. This is not actually as large as they are in high redshift when you look at things with MUSE, so maybe the CGM is changing between high Z and low Z. That's not entirely surprising. Profiles appear to be closer to exponential than the star-forming regions that produce the Lyman-alpha, where the Saas-Fee index is much more extended, Dvorkula-like profiles. I have a few observations are determining whether the gas is, the ionized ISM, which is the intrinsic, what we call the seed function for Lyman-alpha, is ordered or dominated by turbulent motions, and we find that escape fractions are typically higher in galaxies where the ISM is more turbulent. This could be pointing towards feedback, perhaps, or disruptions by mergers. And that mapping of the excitation or ionization parameter may be indicative that Lyman-alpha transfer is enhanced when you have extremely strongly ionized stars and feedback that can carve channels through the interstellar medium. 44 minutes. I'm done. Who's next? Oh, Johannes has a question.
I was slightly confused. There was one slide with arrow 11, and you say Lyman-alpha over H beta, and this ratio is smaller than 10.
Yes?
Did you really mean H beta in this ratio?
Did I write H beta? No, I meant H alpha. Okay. Did I really say H beta? I must have.
It was on the slide it said Lyman-alpha over H.
This is one of these, there was a discontinuity in astronomy, right? Like at about 2000, everything before then you divided all the emission lines by H alpha. And now we discuss the H beta, and everything after then we start dividing everything by H alpha. So where was that? Here. What did I say? Lyman-alpha over H alpha. There?
No, the next line.
This one? Oh, up. What?
Pixel with Lyman-alpha. 0.3 seconds.
1, 2, 3. H alpha. Oh, it's Mark's turn, or X's turn, or somebody else's turn. Yeah, okay, well then no one's here, so, okay. When it comes on, then, That was about 2/3 of the slides, wasn't it? Which, so,
Figure where you plotted the surface brightness.
oh yeah, that one. I know. This one with the contours, right?
Yeah.
Okay.
So there's that little tail up above the main star.
There?
Yeah.
Yeah?
What is that?
It's that central part there. This is the bright, I mean, on this, you can cut this by Lyman-alpha surface brightness, right? So this is the brightest emitted pixels in Lyman-alpha. And that's this central region here, and that's this not C region here.
Okay.
And here, this is where, I mean, you see the morphology of points here. It's kind of flattish, like an uncorrelated upper end limit to the envelope, and then it turns on this corner here and goes up. And this, because it corresponds so closely to the upper limit set by the case B, then I believe this is, I mean, I don't want to say it's photons that are being emitted directly without any scattering at all, but I think it's a region where the scattering is very much minimized. And you see it's not like a line, right? There are points coming down and dropping onto the main distribution here, this main cloud. And I think there is scattering going on here, and there is dust reddening going on. That's what's bringing some of the pixels down. But the limit is set by the case B, and I believe that's because possibly because of feedback, possibly because of the very hard ionizing radiation field from here, that there could be a large mitigation of a lot of the scattering, and we could be seeing, not direct, but close to direct emission from this region, Any more questions?